In this video, we'll go over a complete breakdown of all different types of chemical reactions. So we'll begin with the synthesis reaction, also known as an addition reaction. We can have a general formula for this reaction be A plus B yields AB. So that's why this is called synthesis or addition, because we're starting with two reactants and we're essentially adding them together or combining them to get one product in the end. So if we look at an example of this, one can be the formation of magnesium oxide, which is just having magnesium plus oxygen. This will yield magnesium oxide. So we took our magnesium and our oxygen and then added them together. Another one will be a formation of an acid. So we can do a reaction of carbon dioxide with water. So if we have CO2 plus H2O, we're just going to add them together. And we're going to get H2CO3, or carbonic acid. Let's look at the formation of ammonia. So ammonium, we're combining nitrogen and hydrogen. Again, you want to make sure that when you are adding these together, this is a balanced chemical equation. If not, you're going to have your coefficients messed up. So here we're taking our nitrogen and our hydrogen, and when we add them together in our addition reaction, we're going to yield our ammonia. So a common mistake that students make with synthesis is they confuse it with combustion. So we'll get into combustion a little later, but when you see oxygen reacting with another element and only one product forms, that's synthesis. As you'll see in some later examples, when oxygen forms carbon dioxide and water, this would be a combustion reaction, which is a completely different type of reaction. Now let's look at some decomposition reactions, which is the complete opposite of our synthesis reactions. We're going to start with one compound and we can break it apart into two or more simpler substances. So these reactions usually require heat, light, or electricity, some form of energy, in order for them to occur. So we can say that this would be AB yields A plus B. And typically on the arrow or the yield sign, you'll see an HV or a delta H or something similar to indicate that there is heat or light that's being added. So to look at some examples, we can do the decomposition of hydrogen peroxide. So hydrogen peroxide is H2O2. And in this balanced chemical reaction, we would have two of them. That will yield, we'll say with light, that'll yield 2H2O plus O2. So again, this is the complete opposite of our addition reaction. We're starting with only one compound and we're breaking it up into two smaller or two or more simpler compounds or elements. Let's look at another example. We'll do the decomposition when calcium carbonate is heated. So we'll start with our calcium carbonate, our CaCO3, and this will break up into two more simpler products. In this case, it'll be CaO and CO2. Again, you want to look on both sides, make sure that everything's balanced. We have one carbon, one calcium, and 3 oxygen on both sides. So now let's look at the electrolysis of molten sodium chloride. So when we take our sodium chloride, it breaks up into sodium metal and chlorine gas. So if we have 2NaCl, our sodium chloride, this will break up into our two ions. We're going to get 2Na plus Cl2. Now let's move on to single replacement reactions. For a general formula, we can say A plus BC yields AC plus B. So it's called single replacement because we're replacing one of our elements with another. We're essentially swapping. One's going into the compound, the other one's just becoming an individual element. So in our general formula, our A and B swap places. So our A goes into the compound with C, and our B comes out and stays as just an element. Here's the important part about this. It only works if the incoming element, so in this case our letter A, is more reactive than what's in the compound, so B. This is why we would use an activity series. So for metals, a more reactive metal will replace a less reactive one, and for halogens, a more reactive halogen will replace one that's lower on the periodic table, one that's less reactive. So let's look at a metal replacing metal example. If we have zinc plus our copper sulfate, will we have a reaction here? The answer is yes, because our zinc is more reactive than our copper in this case. So our product would be copper by itself plus, now it's going to be our zinc sulfate. If we had it the other way around and we had copper plus zinc sulfate, what would the product be here? We would have no reaction here. Because like we said, the only reason that the first reaction went through with the single replacement is because the zinc is more reactive than the copper, so it was able to swap it out. Well, now the copper wants to replace the zinc, but the copper is not as reactive as the zinc, so the reaction won't occur, and we can just write no reaction here. If we look at the same thing with a halogen replacement now, if we take sodium bromide, which is NaBr, and say we add chlorine to it, would we have a reaction here? And if so, what would the product be? So in this case, the chlorine is more reactive than the bromine by looking at the periodic table. So we know that this reaction will in fact go through. So the halogen will just replace the halogen, and we will end up with 2 NaCl plus Br2 as our products. Now again, if we wanted to go the other way, so we would have Br2 plus NaCl. This reaction won't go through because the bromine is less reactive than the chlorine. It won't be strong enough to force that single replacement reaction. Similarly, if we have our NaBr and we try to combine it with iodine, would this reaction go through? It would not, because iodine is lower than bromine on the periodic table. It's less reactive. So the higher up we go in the periodic table, the more reactive we get. Since iodine is lower than bromine on the periodic table, that means it's less reactive. Less reactive, it means it's not strong enough for the reaction to go through. Now let's take it up a step and look at double replacement reactions. So a double replacement reaction involves two compounds swapping their ions. Again, not every swap results in a reaction. So we're going to need a formation of a precipitate, a gas, or a water. If none of these form, we'll have no reaction, just like we saw previously. The general formula for this would be AB plus CD yields AD plus CB. So in this case, our B swapped with our D. This is a double replacement because the B is replacing the D and the D is replacing the B. So here we have two compounds and we have one element swapping with another element from another compound, whereas in single replacement, we had one compound and one individual element that was being swapped. So if we apply this to an example, if we have silver nitrate reacting with sodium chloride, which would be AgNO3 plus NaCl, we would get AgCl plus NaNO3. Very important, you want to make sure to match the correct ions. So we write the cation first, the positive charge, the anion second, or the negative charge. So our silver will have a positive charge, nitrate has the negative charge. The sodium has the plus charge, the chlorine has the minus charge. So the plus charge will go with the other minus charge, this minus charge will go with this plus charge. Now, why does this work? It's because silver chloride, which we get as one of our products, is not soluble, so it becomes a precipitate. And again, we need either a precipitate, a gas, or a water to form. So the reason why this one works is because a precipitate forms. Another example would be an acid-base neutralization. So if we have hydrochloric acid, HCl, and we mix that with sodium hydroxide, we would get this plus hydrogen minus chlorine plus sodium minus hydroxide. The plus will go with the other minus, so we get HOH, which we can reorganize that into H2O. So we get H2O plus our NaCl, our table salt. The reason this one works is because one of our products is water. It's H2O. So if we have sodium carbonate, which is Na2CO3, and we add that with our hydrochloric acid again, our products here will be our NaCl, but we're going to get some more products. We're going to get H2O and CO2. Well, now we got more products than what we started with. So you might think that this might be a sort of a decomposition because we're starting with a certain amount, we're ending with more substances than what we started. Well, let's see what really happens. So we have our sodium, which is our plus, our carbonate, which is our minus, the hydrogen, which is the plus, the chlorine, which is the minus. So again, our plus and minus will go together. That's how we get our NaCl. And then here, we're going to combine these two and get H2CO3, or carbonic acid. Now, carbonic acid is very unstable. So right when this forms, it's going to break down into H2O and CO2. So what we actually have with these two products is the double replacement of the H2CO3, but since it's so unstable, it further breaks down into H2O and CO2. So here we have our water that's driving it forward, but we also have our carbon dioxide, our CO2 gas, that's driving this double replacement reaction forward. Now, if we look at combustion reaction, a combustion reaction is a reaction with oxygen that produces heat and light. So a lot of times you'll see it with hydrocarbons. So if we have in a general formula our hydrocarbon plus our oxygen, we end up getting carbon dioxide and water here. So the products, you'll see carbon dioxide and water will also have heat and light, also known as a flame, or when you see fire. That's a combustion reaction. So we have our hydrocarbon and we add our oxygen to it. We end up with our carbon dioxide gas and our H2O, our water, and the heat and light, which is the flame or the fire that forms from this. So if we look with a small hydrocarbon, let's say methane. Methane is CH4. If we react this with oxygen, we get CO2 plus H2O. Again, you'll see hydrocarbons reacting with oxygen, and your products are going to be carbon dioxide and water. These are the key aspects of a combustion reaction. Another one would be with ethane, which is C2H6. We'll have two of them plus 7O2. Try to predict the balanced products of this chemical reaction. you would get 4CO2 plus 6 H2O. Again, we know it's a combustion reaction because we're combining a hydrocarbon with oxygen. We're getting carbon dioxide and water. Now, it's not strictly just hydrocarbons that are used in combustion reactions. We can also use compounds that have hydrocarbons as a part of them. One example are alcohols. So if we take methanol, which is methane with an alcohol group or an OH group attached to it, and we react it with oxygen, we can still use our combustion equation for that. The only difference is, instead of it just being a hydrocarbon made out of hydrogen and carbon, we would have CH3 with our OH, with our alcohol group. This is methanol. If we combine this with our oxygen, again, make sure that the equation's balanced, we would get 2 CO2 and 4 H2O. So it's really important that when we're not talking about strictly hydrocarbons, in this case we have an alcohol, to account for that alcohol when you're balancing the chemical equations. It's also important to note that there are cases where there's an incomplete combustion that occurs, which means we won't get the full results almost always when the amount of oxygen we have is limited. So sometimes, instead of having a product of CO2, we might see a product of CO, carbon monoxide. Or an extreme limitation of oxygen, we might just see the carbon, but we will see the water in both of these cases. So when we have very limited oxygen, if we have our methane again, and very limited oxygen, we might only end up with carbon monoxide instead of carbon dioxide in our water, or just carbon by itself and the water. Now let's look at a more complex type of reactions, the acid-base reaction. So in the future, I will have a separate video outlining strictly acid-base reactions in complete details, but for now, let's just do an overview of what these reactions actually are. So acid-base reactions are a specific or special case of double replacements. The acid donates a proton, and the base provides hydroxide, which we saw earlier was OH. Our products are always going to be a water and a salt of some sort. So the main skill here is balancing our polyprotic acids and recognizing weak versus strong acids, which again will be outlined in a separate video. So if we look at a monoprotic acid, if we have HCl, or hydrochloric acid, and we combine that with sodium hydroxide, what we're going to have is our double replacement. Our Na, our plus charge, goes with our Cl, the minus charge, and then our hydrogen goes with the hydroxide, giving us H2O. We have our water and our salt. Sodium chloride is just table salt. Looking at another one, this is with a polyprotic acid. So we have multiple hydrogens here. So we're going to have H2SO4, our sulfuric acid. We're going to combine that with our sodium hydroxide again, our NaOH. The exact same thing is going to happen here. We're going to get Na2, just to balance it, Na2 SO4 plus 2 H2O. Since sulfuric acid has 2 protons, we need 2 of these hydroxides, that's why I had to go back and add it in order to neutralize it, because we have to do it once for the first hydrogen, do it again for the second one, and then we're just left with our SO4. Try this one on your own. If we have hydrocyanic acid, HCN, reacting with NaOH, or sodium hydroxide once again, what would the products of this reaction be? So we would have our NaCN form, and then we would have our H2O form. Again, we get our salt and our water as our two products. This will always be the case in our acid-base reactions. If this video has helped you at all, please consider liking and subscribing. If you would like to see a more detailed video outlining each of these specific reactions, you can click on the description. I have video links for each of these reaction videos there. Thank you for watching.